Now I'm recording. So we have the given. We know what we want to find. Let's draw the illustration and see. We have this beam. Looks like this. At one end, we have, I think this is A. And then we have a moment of A there. Then we also have, we can take away the pulleys. We can just have force of the pulleys, or the force on the pulleys onto the shaft. And we could do that fairly easy because we've done free body diagrams before. We could put a coordinate system on here. Like that. Now, the way we did it last Friday, we can obviously do that again. We can use the integration method, but with that, it takes too long for some things. For this thing, obviously, reasons it'll take a lot longer than it should. So what we need to do is we can break this up using superposition. So we focus on this one, the application or the displacement at point B, and the displacement at point C, using each force independently. Then once we figure out the displacements at B and C with relative to what's going on with force 1, we would do the same thing with force B and C relative to what's going on, force at 2. So that's the overall strategy with superposition methods. So if we do this, we're going to break this up into different cases. So case 1 looks like this. And that's it. So with that, we still have this force area and this moment. So let's talk about this. Right here, what's the displacement going to be? Right?
Zero.
What?
I guess 0.
Yeah, it's 0. The slope is also going to be 0. So if we use this with just this case 1 of this load P on this cantilever beam, what's going to happen to this? And I'm going to overemphasize this curve. It's going to flatten out. It's going to curve down. And right here, after this, it becomes linear. So this region here is a linear region.
That's linear because
what?
That's linear because only P1 is applied.
Yes, for this case, only P1 is applied, and it's kind of like if I'm standing here, nothing, and I'm assuming it's weightless too, or weight doesn't matter relative to P1. It's just hanging off. Does that make sense?
Yeah.
So we need a couple things. One thing is we need to know what this is. And this is, we're going to call the displacement at B, case 1. That's just labeling. At the end, we need to know the displacement at C, at case 1 as well. Does that make sense? Maybe. Maybe. Anybody?
Yep.
What's the importance of knowing the displacement at C for case 1?
Yeah. What'd you say?
What's the importance of knowing the displacement at C for case 1?
Because first of all, I'm looking for the overall displacement at C. So I need to know case 1, the displacement at C, and case 2, which we'll get into a second. And then I'm going to add them together using superposition.
Okay. Thank you.
No, that makes sense?
Yes.
Perfect. All right, so I'm going to stick with case 1. So case 1, if I draw, and here's where some students get confused, is if I draw a dotted line, a straight dotted line, horizontal to this x-axis, you have this space right here, which is actually VB1. Then you have this place here, which is this angle here, theta, times the length. In this case, it's B. Does that make sense? It's pure geometry. So if you look at a line, it's just the line. And again, these are small angles, so I can approximate where this is B, this is theta, that distance here is theta B. Does that make sense? B is the distance, A is the angle. Yes, no?
So you'll use trig to solve for theta B and add that to the displacement of B to get the displacement of C.
Yeah, I need the angle, this angle here.
Okay.
And I use that angle multiplied by B, because that's linear at that point. Does that make sense, Connor?
Yeah, that's good.
Okay. So now I need to kind of aggregate all of this. So if we go to, we want to find, so the solution looks like this. We want to first find VB1. Now again, we can sit there and we can use the integration method, but we have something easier. We have a thing called tables. So if we move the tables, or if we move to the tables, we're going to get, let's see, I'm going to switch this to Chrome. And if we move to the tables, does everybody see that? Yes, no?
Yes.
Okay.
Yep.
So we're looking at cantilever beam. Here's where some students get confused too. If you look at this and just look at case 1, from here, from A to B, we're going to use number 7. We're going to assume, because this is linear, we use this VB1, the general equation. For this is a deflection, the Vmax deflection for case number 7 for the cantilever beams. So we find out, we're going to put the general equation here, and we're going to say Vmax is equal to minus PL cubed over 3EI. So this is the general equation. Does that make sense? Again, this is just, I'm sorry?
It makes sense.
Okay. So with that, we have to use this general equation. We're going to have to kind of morph it into what our knowns and our variables. What's the first thing you see? So we can say that the displacement. I'm sorry?
Can you go back full screen? I just see your computer
Oh,
right now.
thank you. That would be good. So what I did was here. Thank you. So let's get caught up. So we want to find the displacement at B1 first. Then we use the table 7, and this is the equation V max is equal to minus PL cubed 3EI. This is just right off the table. It has nothing, we didn't map it into our variables yet or our numbers. And some things are still unknown. So let's start to map out this. So we know the displacement at B1. The way I would do my positive y-axis, so it's negative. I use my load, which is P1. And then what's my L? My L would be that A. So I have A cubed divided by 3EI. Does that make sense?
Yep, makes sense.
So what's the only thing missing here? We have P1, we have A, we have E, but what's the I?
Use the diameter to find that.
Yeah. So we would do kind of an aside. And we would say the I is equal to pi over 64 d to the 4th. That's the second area moment for a circular shaft.
You're off screen now for me.
Yep.
I can see it. Never mind. My bad. I wasn't full screen.
I may be off screen, but as long as you can see Lee, can you see that?
Yeah, that works. Thank you.
Awesome. So we get a number, and the number is actually in, let's see, 0.1198 inches to the 4th. So now we know P1, we know A, we know E, and we know I. So we can figure out a number for that. So if we put it in our calculator, we can say that it's going to be negative 0.0192 inches. So about 20 thousandths of an inch it deflects just from P1. Does that make sense?
I got a quick question.
Yeah.
That's negative p sub 1 to the, what's the exponent on that?
Oh, that's a mistake.
Gotcha.
That was,
Appreciate it.
yeah. It's hard to erase. I can't, how about that?
Oh, yeah, it's all good. All good. Just making sure. Thank you.
Anytime. So,
I have a question as well.
yeah.
Is that 0.0192? Is that in like linear inches, radians, or
Yeah, they were talking about displacements.
okay?
So they're going to be in inches. So if we work out the units, we have the pounds multiplied by inches cubed divided by a pound per inch cubed times inch to the 4th. So we're left with pound inch squared on the bottom. Divide by that and you get inches. Good?
Yeah, that's good. Thank you.
So now when we come to the theta now, we're going to take theta max. So the next part is to find VC1. Now, the overall equation for VC1 is going to be equal to VB1 plus that theta we're gonna get from the table times B, which is the distance between B and C. Any questions on that? Okay. So we need to find theta. So we can take theta max from the table. And we get minus PL squared over 2EI. Again, this is the general equation right from the table. We don't know anything. We need to morph that back into what we do or what we know.
Do you have a link to the table from the or on the page?
Yeah, that's a good question. I could take a screenshot and put it in there. That's thank you. Who said that?
It was me, William.
Oh.
I was thinking that would be really helpful for the homework.
No, you're absolutely right. I can do that next time. I'll put the link in this. I'll put the link in the handout.
Okay, thank you.
Thank you. That's really good to. Yeah, that's awesome. So what we can do is this is the general equation for the theta max. That's for a cantilever beam taken out of table 7. So again, we need to put that into terms that we understand. So we map that into, we have theta. Our P doesn't change. We have minus P1. Nothing to do with the B side yet. We're still just looking at from A to B, and we're trying to figure out that theta. So minus P1. So we still have A squared divided by 2EI. And we can get an answer for this. Now, what's the answer going to be in? What units is the answer going to be in?
Radians?
Yeah, that's a good guess. Usually that's the case. And the answer for this is, it's going to be negative 0.0029 radians.
Is that negative? Is that negative infer clockwise?
Yeah, if we draw, Connor, can you see this?
Yeah.
That way is going to be negative.
All right, cool. Thanks.
It's still the right-handed rule. As I stated before, I forget the counterclockwise and clockwise. That always confused me. I think it positive.
All right, cool. Thank you.
So now we can put that into our equation because now we know VB1. We know the theta that is caused by 1 times B. And we should get an answer which is negative 0.0623. And that's in inches. So this is only the start of our problem.
Can you read that answer out one more time? I can't see it.
You can't see this?
Yeah, that one.
Yeah, negative 0.0623 inches. It's also, if you follow along, or if you can, it's also, there's a solution to this online already. Any questions so far? Yes.
I've got a question.
Yeah.
On that I aside, is that d to the fourth?
Where?
On the aside for the I,
Yeah.
is that d to the fourth?
Yes.
Okay, all right, thank you.
Is that hard to see?
It's just a little blurry.
Okay. Yeah, I'll try to make it larger
Thanks.
next time. Sorry. So you still got a couple minutes. Let's start to look at developing case 2 now. I'm going to draw the free body diagram. And we're assuming, well, we're not looking at the force at P1. We're ignoring that for now, and we're just looking at the force on the pulley number 2. So the curve's a little different, slightly. We know the deflection of the curve at A is what?
0.
0. Comes around, so is the slope. So I know it deflects at the end, and that's VC, and that 2 stands for the case. We're looking at case 2. We also need to know what the deflection is at B in case 2 as well. And we'll get to that next on Wednesday. We ran out of time. Anybody have any questions?
Yeah, I got one. When you were solving for theta b,
Yes.
you multiplied the theta as radians times b. Why'd you use radians and not degrees?
Degrees is when you multiply a distance to degrees, it doesn't make sense. It's always in radians. Radians is a no value. It's just a ratio of two lengths.
All right, that helps. Thank you.
And that was just math. That's one reason why it's when you think of degrees, especially mechanics, and I can't speak for electricity or anything, but in mechanics, an angle is just a ratio of 2 lengths. I don't know why they teach it differently in math, but maybe because I'm biased towards mechanics. But anyway. So, yeah, that's why I did that, Lee.
All right, thank you.
Anybody else have any questions?
Can you move just a little bit so I can get the rest of the case?
Well, time has ended. It's 9:55. You can start to just get off if you want to, or if you have questions, let me know. I wouldn't mind meeting with the course improvement committee after this, so if you can stay on just for another 5 minutes so we can help smooth the class out a little bit.
Can you hear me?
Yeah, I can hear you, Hayes.
Did you say yes?
I can.
Okay. I think maybe like the green is kind of hard to see.
Okay.
So maybe if you could increase lighting in the room, I guess you have a window. So when you stood on the left side, like you couldn't see. It was kind of dark and blurry.
Oh, wait. I'm seeing. All right. So if I'm on this side, it's dark and blurry.
It was before. Like your shadow was.
Yeah, that's fine. That's good to know. That's excellent to know. Yeah.
And I don't know if you saw, me and Alex were on the same. We used his video cam. It's easier if we have a second monitor to like actually put the problem on. So I don't know if you want to relay that information to the rest of the class.
It would be. I see what you mean. Yeah, that's a good call.
That's what we're gonna start doing is like putting the actual work and the documents you send on the second monitor.
Okay.
So that way we can keep our video cam up and see the work that you're doing.
Okay.
Yeah, because it's really hard to like window mode both of them. So I pulled that too as well.
Okay.
I would say
Not
one
doing
thing is,
breakfast to go.
I would say the important thing, like make things that are important